The working principle of Kaplan turbine. The coupling turbine is a pure reaction turbine. You can see the cut view of coupling turbine. The water comes to the casing, where the casing is designed in such a way that the cross-section area starts decreasing so that the velocity of water remains constant all the way to this flow, and finally then goes to the inlet guide vane where the fluid or water then passes to the runner, and finally it comes out from runner. Since it is a Francis turbine is a axial inlet and axial outlet turbine, and it is also pure reaction turbine, so pressure drop occurs only in runner blade. The turbine is designed in such a way that the cross-section area of the turbine outlet is lesser than inlet, and due to this the velocity of fluid is more than inlet. The exit high velocity of the fluid from the runner blade causes reaction to the blade, which helps the runner blade to rotate, and this is called the reaction of fluid on the blade. The coupling turbine is used for relatively lower head and higher flow rate as compared to Pelton wheel turbine and Francis turbine. Kaplan turbine is a axial inlet and axial outlet flow turbine as shown here. So you can see here the casing area is larger at inlet and this side is smaller, so it starts cross-section area starts decreasing, and after coming out from the IGB the flow becomes axially at inlet to the blade and axially outlet from the blade. So these are the IGB and these are the blade, runner blade. So high head water comes from the reservoir to inlet guide vane through the casing of turbine. Casing is designed for decreasing cross-section area to have constant water velocity. Then water travels to IGB. The main function of IGB is to control the flow through turbine. Water coming out from the nozzle or IGB strikes to turbine blade axially. You can see strike the blade axially. Water further travels to runner blade where pressure drop occurs. Here pressure drop occurs here, and due to drop in the pressure, high velocity of water comes out from the blade. High velocity coming out from the blade, which creates reaction to the blade and helps in rotation. The water comes out from the runner blade is axially, which is shown here. So typical construction of coupling turbine is shown here on the right side. Francis turbine is a radial inlet and axial outlet turbine, and this is a schematic view of a runner with blades. Coupling turbine blade can be fixed or movable type based on the design construction. In case of movable type blade, when flow is minimum, blade tries to become closer to horizontal. When flow is minimum, this blade rotates and try to become horizontal. But when flow is maximum, blade tries to become closer to vertical axis, and this is done to have a proper angle of fluid striking to blade and to have minimum losses and maximum efficiency. Now the coupling turbine power is associated with mass flow rate, hydraulic head and hydraulic efficiency. Turbine power is mass flow rate into hydraulic head into hydraulic efficiency upon 3600 into 1000 bracket close. So turbine power is equal to, further we can write in another way, volumetric flow rate into density into hydraulic head into hydraulic efficiency upon 3600 into 1000. So turbine power P is equal to Q into RD into HS into ES upon 3600 into 1000. So P is turbine power kilowatt, Q is a volumetric flow rate meter cube per hour, RD is density of fluid kg per meter cube, HS is hydraulic head joule per kg, and ES is hydraulic efficiency, which is constant. So hope you understand the working principle of coupling turbine. So thank you for watching.